Hello everybody and welcome to NPTEL certification course on cryogenic electronics for quantum computing. This is lecture number 52, and in this lecture we will be studying quantum entanglement and quantum communication. So let's look at the outline of the talk of this lecture. We will look into entanglement. We will again then have the difference between classical communication and quantum communication. We look into quantum teleportation, very brief idea. There is a huge topic which deals with quantum communication and superdense coding, and then we will look into quantum key distribution and then see some highlight some real world applications attached to it. So what is entanglement? Well, this is quite a funny sort of anecdote or a funny idea which is there, that basically entanglement implies that there is a quantum correlation between qubits, which means that if one qubit state is fixed at a distance, the other qubit somehow or other knows and tries to fix up a state instantly at that point of time. So if you measure the measurement of one of the pair, within a pair, let us suppose I have two bodies here. If you measure the state of one of them, the state of the other is instantly known to you, right? And this is quite an interesting one because this is sort of an action at a distance approach which is being done, right? So which means that if you have, let us say you are doing entanglement, you are doing a small change in the qubit direction at Earth, let us suppose, and the qubit is kept in the moon, one of them at such a long distance. So if you change the state here, you would be instantly able to determine the state of the qubit at a distance, right? And therefore there is a correlation, quantum correlation between various qubits. Now, how do you create an entanglement, right? So basically we use Hadamard and C0 gate. So if you see very carefully, we use Hadamard and C0 gate, right? So this is, let me change the color of the, so we use Hadamard and C0 gate for designing it. So let us, example circuit is shown on the right hand side, right? I am sending a qubit 0 and a qubit 1 through an Hadamard and then through an X gate poly, and then this is the qubit state which we are referring to. So if you apply H gate to 1 and apply C0 gate, and so basically the control qubit is 1 and the target qubit is 2, right? And we need to find out whether there is an entangled pair coming into this picture or not. So let's look at the fact that by applying this H gate or Hadamard gate and the C0 gate, do we actually get an entanglement pair? Now let us suppose that both the qubits start with 0, let us suppose, right? Your ket vector is 0 in this case. And then the initial default state will be Q0 will be 0 and Q1 will be also equals to 0, both are 0. And therefore, when you take the two states together, the state will be 0, 0, correct? So the final states which you gather or have without entanglement at the initial stage is that it is both states are 0, 0 in nature. Now let us apply Hadamard gate to qubit 0. Now as you can know, Hadamard gate puts 0 into a state of superposition such that Hadamard 0 is equals to 1 by root 2 ket of 0 plus 1, right? And therefore, if you want to find the total state, it is basically, so this state is coming from H, so I will get H of 0, right? And you are trying to manipulate this with 0. And therefore, what will happen is this can be broken up into, as you can see, it is 0 plus 1 here and this is 0. So you will get 0, 0 as one state, which is this one, and you will get 0, 1 as then 1 is 1, 0 another state, you get another state. And so you can think this as a qubit 0, right, being both 0 and 1 at the same instant of time, and qubit 1 is still 0. So qubit 1 is still 0, but qubit 0 can be either 0 or 1 at the same instant of time. That is the reason we define this to be as this, right. The qubit 1, if you see very carefully, it is still 0. So, I have still 0, 0, but qubit 0 can have 0 or 1 bit, right. Now, if you apply C0 gate, which is almost like a conventional NOT circuit, inverter circuit, C0 gate, then control is equals to qubit 0 and the target, let us suppose, is qubit 1, right. Which means that if the, which effectively means that your control is 0 qubit and the target is qubit 1. Now, if qubit is 0, right, if the qubit 0th state is 0, then you do nothing to qubit 1. So, if the 0th state is at 0 state, then you do not do any operation on qubit 1. However, if the qubit 0 is 1, then flip qubit 1 from 0 to 1. You got the idea? And this is the reason we define this to be as a NOT gate. So, if you apply the same state, so if it is 0 0, since by my definition if the state is 0, I do not change my 1th qubit and it stays therefore at 0 0, because qubit 0 is still 0, you see this part. When it is 1 0, that means when qubit 0 is 1 value, then I change the state of 1 to 1 1, and therefore qubit 0 is 1, therefore flip qubit 1 to qubit 1, and therefore you are left with what? You are left with 0 0 state. It is a superposition of 0 0 state and 1 1 state. When you apply C naught circuit to this C naught gate to this circuit, right, it is 0 0 and 1 1. Now, so you get what? You get 0 0 state 1 1. Now, what we have done effectively is, and that is what I was showing you here, that if you have an entanglement state, then we define this to be as phi plus, then if the first qubit is 0, the second must be 0. If the first qubit is 1, the second must be 1, right. That is what it is stating here, which means that if you know this state is known 100% and this state is known, this state is known. This is basically known as entanglement, and therefore and this cannot be defined by classical product states, right. And therefore, if you want to measure one qubit, it gives me the answer about the other qubit, that if it is 0, you surely know that it is 0 there. If it is 1, you surely know 1 is there in the state of entanglement. And this gives me a brief idea about the basic concepts of entanglement theory which is being applied here. Now, let us come to the classical communication systems, and we will try to compare a classical communication with quantum communication. Now, in a classical communication, the user, let us suppose this is Alice and this is say James, right. So, Alice sends a signal, request signal to James, and James sends a response back to Alice, right. So, you see this is the response it is sending and this is the request it is sending. So, if there is no request, there will be no response. Now, that is what is written here, the sender initiates a request to send the data and the receiver sends a response confirming the readiness to receive the data. Now, typically what happens in any communication system is, this is first handshake which you do. The second handshake is when once you send the data and the data is received by the receiver, then also it sends an acknowledgement that the receiver has received the data, confirming the receipt of the data, not the readiness to confirm the data, receive the data, but its actual receipt of the data is confirmed by the receiver, which is in this case James. Now, so this is the general idea. If you go slightly on the much more detail of it, then typically on the sender side you have a modulator. You input your data and the modulator gives you a single signal output. This signal output, there is a multiplex channel, you can send it through air. If it is a wireless part, you can send it through fiber optic. If it is a optical communication, then you do a demodulation here in the input side, you do a modulation at the output side, the signal, there is a multiplex channel again at the output side, and the demodulation is done again here, and whatever the signal you are feeding here, you get the corresponding data output at the receiver side. Fine. So, this gives you a brief idea about general communication theory which you see, which means that you have an input modulator and a demodulator. So, you have the input side you have a modulator, at the output side you have a demodulator, and therefore there will be multiplex channel available to you for the signals to go throughout. Now, again there is something known as routing and hop by hop forwarding. The signal travels hop by hop through intermediate nodes in a multiplex channel. So, if there are multiplex channels, it flows from one node to another from there. For example, in optical communication, let us suppose it flows from one multiplier to another multiplier to another multiplier, where the signal gets multiplied because there will be heavy attenuation, right. So, these nodes demodulate and remodulate the signal for forwarding. So, these individual nodes which you see here, they will be actually demodulating and modulating at every point of time, and the signal moves forward from the sender to the receiver. And at the receiver end, there is a demodulator which converts the signal back into the data, right, and the data is finally given to the output. So, this is the basic idea about the classical communication which we do, and so there are various techniques available by which you can do all these things. Now, you can replace this multiplex channel by multiple things. For example, you can actually do a large amount of the mode of, for example, wireless, optical, and so on and so forth. The node can be multiple things, modulator and demodulator also can be of multiple things. Now, let us look into quantum communication, right. Again the same concept, Alice and James, but what happens is that you have a sender now, this is the sender here, right, who is the Alice, and this is the James who is the receiver here, right. Now sender will send a request, of course, as to initiate quantum communication, and the receiver send an information to confirm participation. It might also happen that the sender sends an information, but the receiver does not want to communicate back. Then the sender will not send any response back to the receiver acknowledging that he or she has received the request. Now in the sender module, this sender module, there will be a quantum transmitter, right, which prepares the qubit in entangled states by principle of superposition, and then these are sent over from the sender to the receiver through a large amount of quantum channels. Now the quantum channel can be shown by this dynamic channel here and dynamic channel here, right. It's a two-way communication platform by which you can actually send the data from sender back to the receiver and receiver back to the sender, and it's a two-way communication which you see, and this is primarily based on entanglement linked resources. So you obtain a link resource which is entangled, and you send the entangled data from the sender to the receiver and back. Now how to do routing and entanglement link setup. Now instead of data packets, the network creates large amount of entanglement between the intermediate nodes. So which means that if you have say that you have 4 intermediate nodes, then by the understanding of entanglement theory, you very well know that if you are able to predict the state of the qubit in any one of the nodes, you will be able to predict the state of the other qubit which is traveled at other nodes which is forward of them, right. So this is basically known as entanglement which is happening. And there are large amount of quantum channels are established, and this is known as dynamic allocation of quantum channels. You need to be very careful that you need to maintain appropriate bandwidths and fidelity of the channel, and this to be monitored in real time so that the states do not get affected by the bandwidth restriction as far as the communication link is concerned. So now we have sequence, nested or parallel swapping methodology, and then 3 types of entanglement swapping techniques. These are known as sequential, nested and parallel. And if you have subsequent 2 qubits being done, we define that to be a sequential. Nested, parallel means if 2 are in the same state, they can be parallelly combined to each other to form the entanglement swapping in case of quantum communication. If you look at quantum, therefore teleportation, once end-to-end entanglement is set, means which you know from the user to the receiver or the sender to the receiver, the whole network is entangled, and you know very well that the entanglement has been properly done. You just need to teleport the quantum state from to the receiver, either using entanglement theory or classical communication. Obvious classical communication is a state we already know, but you can also do it via nested or swapped entanglement. Now the problem is after the sender the receiver, or in this case the receiver receives the information, it again needs to send back result feedback, which is point number 6 here. So you have a quantum teleportation from Alice to James, and then there is a back result feedback from James to Alice saying that the data which was sent by Alice has been received properly by the receiver. Now you see what is the advantage of having a quantum communication. The advantage here is that since they are entangled, the data is heavily secured in case of quantum communication, right, and it's very difficult to actually change it, because as you just try to read the state will change itself at the very instant of time, right, and therefore there is a big research going on around the world on quantum communication, initially at short haul and then and as we proceed forward on a long haul sort of network. Let's look at quantum teleportation, and this is exactly the same as I was discussing in the previous case, that if you want to transfer an unknown qubit state using entanglement plus classical bit, then we define that to be as a quantum teleportation. Now let us say in this case example is we have an Alice and Bob who are basically share an entangled pair. So they share an entangled pair means if Alice has done a measurement at her qubit state, then she can predict what will be the state at Bob. Similarly vice versa, Bob is predicted the state at his own end, he will be able to predict the state of the Alice's qubit. Now if Alice entangles her qubit with the unknown state, she measures and sends the signals bits to Bob. Bob will apply gate to recover the state. You got the point? So what will happen, how does it work out is something like this. This is the communication link, classical communication link, and this is the entangled states between state A and state B. There is an entanglement state, entangled states comes into picture. This is the input state which you are doing, this is the output stage which you do. What you do basically is that Alice will at her end, she will entangle her qubit with an unknown state, and then she measures, and once she measures this and sends it a classical bit to Bob, then Bob will apply proper gate. What gate? Hadamard and C naught to in order to recover the state. So this is how you can actually do quantum sort of teleportation from point A to point B. Okay. Now let us move slightly into the different domain of coding, and that is what is known as super dense coding. Is basically a quantum communication protocol, right? This is and what it does is it sends two classical bit by transmitting only one bit using a pre-shared entanglement. So you know, if you know a pre-shared entanglement, you can transmit one bit and there will be sending of two classical bits will be allowed, right? And however, the requirement here is that there should be a quantum entanglement between the receiver and the sender. So that quantum entanglement between the sender and the receiver has to be maintained at all cost. And if you look at this diagram which is kept at the below, you will see that you have a bell pair here. I have a Hadamard gate and a NOT gate. I encode the bit using an external entanglement. I send it to the receiver de-entangles and gets the classical value of bit 1 and bit 0, right. And this is super dense coding which you do, it is very fast and very efficient in the sense. Now let's again break down the steps into various protocols. So the Alice will send the classical message and Bob will receive the message. Now let us say a third party comes into picture and we name him as Charlie, let us suppose, and the third party who prepares and distributes the entangled bell pair to both Alice and Bob. Now the sources for the first step, which is basically to prepare and share a bell pair, Charlie shares a bell pair using a Hadamard and C naught gate, which we have already discussed in our earlier slides. One of the qubit is sent to Alice and the other to Bob. Once this entangled pairs, once you generate an entangled pair, you send one to Alice and one to Bob, then each state is known a priori to both of them. Now as I discussed with you, Alice then encodes the two classical bits, right, and based on the message bit, which is bit 1 and bit 2, Alice applies I gate for 0 0, Z gate for 0 1, X gate for 1 0 and XZ gate for 1 1, right. And therefore, these gates will transform the bell state accordingly. What is the bell state? Bell state is 1 by root 2, right, 1 by root 2, and this is 0 0 plus 1 1, right. This is the bell state which we have already seen in our earlier discussion, right. This is equals to phi star get, right. Then after encoding, after you encoded using these schemes for 0 0, it is I gate, for 0 1 Z gate, poly Z gate, for 1 0 it is poly X gate, and for 1 1 it is XZ gate. Then what does do is that Alice sends a qubit to the Bob when you transmit it to the Bob, right. And then the step 4 is the Bob then decodes the message by doing the reverse of it. He applies a C naught gate and a Hadamard gate. So initially you did a Hadamard C naught, now you do a C naught Hadamard, and he measures both the qubit to obtain the classical bit B1 and B2. And therefore the final result is that Bob successfully receives the two classical bits, whereas Alice said only one qubit but transferred 2 bits for classical information. So the idea here was that you have one qubit which Alice has done, but because of quantum entanglement, Bob was able to retrieve the two classical bits in a very easy manner, and this is known as the super dense coding which you see in this case. Let us come to the final part of one of the later parts of my code, and this is known as the quantum key distribution or QKD. Now QKD is a secure, this again, so just like the super dense coding, QKD is again a secure communication protocol, and that uses quantum mechanical principles to distribute the encryption key. The whole idea is how will you distribute the encryption key, and its basically advantage is that if you do any eavesdropping means any external third party tries to attempt to disturb the channel or extract information of the channel, this will disturb the quantum system and it can be easily detected, right. So the key features of this are based on there is no cloning theorem and the measurement disturbance is not there. It provides unconditional security, unlike classical cryptography which depends upon mathematical hardness. This provides a unconditional security in terms of entanglement theory. As I discussed with you, it involves two channels. One is the quantum channel which transmits photon encoded with key, and you have a classical channel which does the key verification. So two channels are available to you. One is known as the quantum channel another is another classical channel, and it gives the quantum key distribution gives you a much better secured channel available to you for all quantum communication purposes. Now let me give an example here. Let us say Alice is sender who wants to securely send a key to Bob, who is the receiver. So what we do, we use a quantum QKD channel. Let us suppose I generate a random secret key, right, which is shared between Alice and Bob using quantum communication. So this is the random key, this is the random key generated. I have a message, Alice sends it to through an encoder, right, and this is your encoded message which goes, this is an insecure channel, this is a random secret key goes through the QKD channel, and this is the decoder at the Bob, and Bob actually decodes the message which has been encoded at Alice and to generate the message signal. And the channel is secured due to quantum principles, because the red colored channel is secured because in any case it is an encoded channel which you see, and can, however, this channel can be intercepted, but the message is encrypted using the key from the QKD. So the QKD key, which is a random key sort of generated, you will never able to intercept any message going through the red channel, which is basically the random secret key which is going there. Now the encoder, this uses the shared secret key to encrypt the message. So I have a secret key available, the encoder actually encodes and shares the secret key, encrypts the message. Decoder does the reverse, it uses the same key to decode the message and recovers the original signal, right. Now what are the key security concepts here? Again, the eavesdropping is almost, if you want to eavesdrop, it will disturb the state of the qubit, so the information will be lost, and this disturbance alerts both Alice and Bob, prompting them to discard the compromise key. So if a key has been generated and the key has been going through the quantum channel, and any one of the eavesdropper third party tries to negotiate that, the information goes to Alice and Bob, and they can actually drop the communication link saying that it has been compromised. Now the problem, the advantage here is only Bob and key, the sender and the receiver, will be able to use the secret key, and this ensures confidentiality and integrity of the communication link. So let us look at the real world applications, and these are basically quantum internet is coming up in a big way. You have satellite QKD, satellite quantum key distribution is there, and long distance secure communication, but we require quantum repeaters to extend the entanglement range. Currently it is very small, but you can actually do physically to a satellite region also in real world applications. So let me recapitulate what we did till now, explain to you what is basically quantum entanglement, right. We also explained the various types of operations which you want to do if you want to use a secure key. Then we went into quantum entanglement, right, entanglement we discussed. Then we discussed QKD, which is quantum key distribution, a secure communication purposes, and finally we actually looked into the final state, which is basically the applications of these things. So these we had taken up, and this takes care of our understanding of the quantum state. A very basic idea, deep study needs to be done in this domain. There are a large number of researchers working in this domain. I hope you enjoyed the lecture. Till we meet next time, goodbye.